Okay. So yeah. So I think you can start. Till now, we have primarily focused on how to solve a reliability analysis problem. And by solving reliability analysis problem, it means that to find out the probability of failure of a system. Now, although I am using the term system, we have not really covered what is known as system reliability. Rather, we have focused primarily on component reliability. So, what we have done till now is talk about algorithms, talk about methods that can help you in solving component reliability analysis problem. And if you think about it, we have broadly classified into three types of method. The first one was based on Taylor series, which included first order reliability method, first order second moment, MBFOSM, and second order reliability method, and so on and so forth. So that was broadly the first class of method that we discussed. The second class of method that we discussed was on sampling based approaches, where we talked about subset simulation, where we talked about Monte Carlo simulation, where we talked about importance sampling, and I said there is also directional simulation and other algorithms we did not talk about them. And that was broadly the second category, which is based on sampling. The third category of method that we discussed was on surrogate model. So the idea is sampling is expensive, Taylor series is inaccurate for highly nonlinear one. So can we have a good trade-off? And the trade-off that we suggested is that can we use a machine learning model to build a surrogate for the costly, computationally expensive limit state function, and then use the surrogate model for doing reliability analysis. And in surrogate based model, we talked about response surface method, we talked about polynomial chaos expansion, and we talked about Gaussian process. Now, all of these three are quite different from each other, and that's why we spent like 5-6 lectures per topic within surrogate model. Gaussian process, we had 5 lectures, polynomial chaos 4 lectures, and yeah, so on and so forth, right? So that is what we have done till now. But what we have done till now is only analysis. What we have done till now is only to compute reliability index. What we have done till now is only to compute probability of failure. But why is reliability important? Reliability is important because you want to make your system reliable. You want to make your component reliable. How will you make it reliable? To make it reliable, you need to make it reliable and or account for this reliability analysis within your design iteration. So ultimately what you will want to do is that you want to design a system that is reliable. Or if I expand it further, you want algorithms that can help you design systems that caters to the uncertainty in the system, that considers the uncertainty into a system, that does not ignore the uncertainty into a system, and somehow take it into account while solving this design problem. So that is broadly the idea. So in the next module, which starting today, we're going to talk about design under uncertainty, or rather I can call it optimization under uncertainty, because how do we design? We design to optimize a certain factor. We design to make a system safe. We design to minimize the cost of construction. We design to minimize the life cycle cost, and all of those together, right? So we like to design. As engineers, we have to design. That's the role of an engineer. But we want to design while acknowledging the fact that whatever we are designing, we don't have complete knowledge. We don't know about the environmental factor that will come into picture. We don't know the exact material property of the system or the component. We do not know the exact boundary condition. The model itself, we might not know exactly. The model might have some assumptions and approximations. And which means at each of this stage, there is incomplete knowledge, which means there is uncertainty. And we need to acknowledge those. And while acknowledging those, we will try to talk about how you can design while accounting for the uncertainty into the picture, while considering uncertainty within your design loop. So that is the kind of the context uh, on which we'll be discussing starting today. Okay. So moving ahead. So now let us start. So we will like to design while accounting for any uncertainty that might be there. While accounting for, we'll like to design while accounting for any uncertainty that might be there. But before we go there, let us first talk about how do we design or optimize in a usual setup. We call it a structural optimization or a engineering optimization problem, but for the sake of this course, we are going to call this deterministic design optimization. They're essentially the same. I'm bringing this term deterministic because that will explicitly state that we are ignoring any form of uncertainty that is there. Okay. So usually in deterministic design optimization, which is DDO, we solve the following optimization problem. And what is the problem? You will want to minimize certain cost function, certain objective function. That is what you will try to do. So which is D star is equal to arg mean D C of D comma X subjected to. Now when you try to minimize something, it is in real life, you do not get a free pass by only minimizing the cost function. You are always accounting for additional constraints that are there. If you want to minimize the cost, you have to also ensure that the system is safe. You cannot say minimize the cost, because if that is the case, then the ideal minimization is that you should not do anything. The cost is zero. You can, but that is same as negative of cost. So most of the algorithms are for minimization. So even if it is maximizing performance, you convert it into some cost, right? So in that case, right? Yeah. So in that case, it will be zero. You don't construct anything, right? Even better if you have a land, sell it, negative. But those are not feasible, right? You have to construct it, you need it, but you want to construct it while ensuring certain constraint, right? And what kind of constraint you might have? One of the constraint might be that h of D comma X would be less than equal to some h threshold, right? And we'll relate it to some real example. And then you might have some equality constraint as well. I'm not writing that, but there can be equality constraint as well. And there can be limits, right? You have, let's say, D lower limit less than equal to D less than equal to d upper limit. More or less, this is what you will work with. For example, let's say I want to design a car. This way you can imagine that I want to design a car that is optimal. Let's say that is my objective. Optimal means cost wise, which will, because I want to target the population that cannot afford a car. So I want to design a car where the cost, selling cost will be less, so that a common public who cannot afford a car can afford it. I mean, that's a good business strategy, I will say, in India. That's it, right? So in that case, we will try to minimize the total cost of manufacturing of the car, subject to that it should satisfy certain safety constraint. If there is an impact, the person should not die. Some comfort constraint also, the person should be comfortable while driving. So there should be some safety constraint, there will be some comfort level constraint or serviceability constraint. And then also there will be probably some limit on the design, like the shape cannot be too small, it cannot be too large. So there is some upper limit, lower limit on the shape, let's say, of the car as well. You can imagine like that, right? So that is how you can relate this one with a usual optimization problem. That's how a design problem becomes an optimization problem. Now, one thing that I've written here subtly without mentioning it is X. X, you can imagine the parameters that are there, but the parameters that you cannot control. So, which means the parameters that you will not design for. Example, let us go back to the car example. Design, I said you were, let's say, designing for the shape. You're designing for some plate or cell is there, the thickness of that and all of those things. But that's material selection can be there, but the material property, you don't control it. Even if you select it, you don't exactly know whether it will be there. So that can go to X. The environmental condition, the load that it will encounter, you don't design. I mean, you cannot control that. So that goes into X. So all of those things, right? Any manufacturing, during manufacturing, any error, or because whatever you design on pen and paper, on your computer, on your laptop will not be exactly manufactured. So that will also go into X. So X are parameters that you don't design, D are parameters that you design, right? So that is what you generally do. Okay. So now, with this setup, this is a deterministic design optimization. There is no uncertainty, nothing is there. And let's say you solve this problem, right? Let's say you solve this problem. In most cases, if you solve this problem, what you will see is that for any problem which is a meaningful constraint, the design variable D will reside on the constraint boundary. Simple, I mean, it's quite straightforward and intuitive. Otherwise, that constraint is not a valid constraint. I mean, that constraint, otherwise that constraint is not valid, because what will happen is that even without that constraint, you will start getting same results. So that constraint being there or not being there does not matter. There can be. Give an example. Let me try to make it concrete with your example. So generally what happens, I'll give you one example. I'll let you tell me that if that resonates with what you are trying to say. Huh. Huh.
In my problem, it was something like near the bound. But when that problem becomes very simplistic in the name.
No, it is not. Why? Because you will not have one constant, you will have multiple constraints. It's never one constant that you are working with. Even in your problem, it will have multiple constraints, right? And you will realize it sits on the boundary of one of the constraints. But you don't know which constraint. So you solve and you will realize that there is one constraint that governs your design, and satisfying that often makes it satisfy the other. In worst case scenario, two constraints will govern the design, and then it will be the intersection of the two constraints.
So in that case, we can just remove the
Yes. Yes. But if it is only one, you don't know. It can be three constraints intersecting, and that intersection point also can be there. But in a practical scenario, it's never more than two or three. The other things has to be there. So what people sometimes do is that they design for one constraint because they know that is the important one, and then they check whether the other constraints are satisfied or not. I mean, that is also done. If you know a priori that this is the constraint that is governing, then only design with that constraint, but do check at the end that the others are also satisfied. You can do the opposite also, then you will realize that the cost increases for one of them. So take the minimum cost one in that case. But yeah, so coming back, what will happen is that in most cases, almost all cases, you will see that the constraint will be another constraint. The design variable, D star, the optimal design variable, will be sitting on the constraint boundary. That means if it goes little bit, it will go to the constraint violation zone, which is the unsafe zone. Which boundary means the contour. Yeah, hyperplane in that case. Yes. Not the boundary condition, obviously. So, yeah, exactly. Yeah, exactly. Okay. So that is what will happen. So if I may draw, or I have a figure actually, let me go there. I generally have 15 slides, so let's go to 17 and see. No, more than that. Yes. I don't know how good the visibility is, so let me make it a laser pointer. So let's say this is where you are designing, right? So look at this brown zone, the darker brown. This is your contour. You can see the circular lines of contour, but not everything is visible. But these lines, right? This is the design variable space. And then this line, this parabolic line is your constraint. And because of this setup, you can see that the optimum point is the blue point here, which is on this constraint boundary. Right? So this is here, which means if there is a small perturbation also, there is a very good chance it will go into this darker brown region, which is the unsafe zone. Right? So that is generally what will happen in your case, which means if you go by this design without accounting for the uncertainty in the picture, there is a very high probability that your system is going to fail. There is a very high probability that your system is going to fail. But in practice, does it fail when you design it? Because in practice, most of the designs, we do not take uncertainty, but also it does not fail. So how are you achieving that? Because in a practical problem, in an industry, when you design it, you do not take for uncertainty, or apparently you think you are not considering uncertainty, but what you take is partial factor of safety, which means the load is coming 5, you say that, okay, let's assume the load is 5 times 1.5. So you increase the load, and now you design for that. So that partial safety factor accounts for the uncertainty in an ad hoc manner without you realizing that has been accounted for. Without that partial safety factor, your system is now designed to fail very quickly, I'll say, with a very high probability, because whatever you are designing, if you are lucky, the manufacturer will manufacture on the conservative side. But in most cases, if it tries to make it exactly, it goes up slightly here and there, it fails. So the partial safety factor is what we account for in actual design. So there is a nominal factor. We multiply the load by that factor and all of those things, and that helps us account for the uncertainty without us needing to know anything about the uncertainty. And those factors are designed for some target reliability. For example, if you want a reliability of 3, then that factor is, let's say, 1.5. If you want 3.5, that factor is 1.75. If you want a reliability of 4, that factor is 2. I mean, these are ad hoc numbers, obviously, I am giving, but you can derive that. It is possible to derive that. This is a self-learning component. It is there in the Halder and Madhavan book. And there is a problem in homework 5 which asks you to do this, to find out this partial safety factor for a target reliability. So in homework 5, which has been uploaded now, there is one problem which talks about reliability based design. Okay, how you can determine a factor for a target reliability and then take that factor, forget about uncertainty and design for that. Okay. So that is how it is usually done. Okay. But that is not economical. And so there is a need, and most high risk industry are now going towards actually incorporating uncertainty without this ad hoc manner, actually considering uncertainty into their design law, not by some factor, but by doing an actual reliability problem or something else. Okay, so that is the whole idea. Any question till now? If not, so what I was saying is that in DDO, DSTR generally sit on the constraint boundary, right? It is generally on the constraint boundary, which means probability of violation or violating the constraint. The constraint is high. This means naturally means this, right? In design, in usual industrial setup, most of the cases at least, this is accounted for by bringing in partial safety factor. Okay. One way to address this is to bring or exploit or use partial factor of safety or safety factor. Okay, which is multiplied to the load, and you consider that the load is 1.5 times of the load it is actually coming, and you design for that in that case, right? You can also do the opposite. You design for the exact load, whatever you design you get, you increase that, make it safer, right? I mean, that also is possible. You can imagine that doing that, and then you call it safety of factor of safety also. Okay.
Also a major challenge in we don't know because that is also totally random.
No, that is not random. So remember at the beginning I said that the thresholds you get from some Indian standard codes, the safety factors are also there in those codes. So at least in civil engineering and in ASME, I mean mechanical engineering also, everywhere there are standards, and they tell you what is the factor to take or what level of design, right? This 1.5 number is from code actually. Okay. But the problem is that they have designed it for some target beta which you don't know. If you want to make it more reliable, let's say, now you don't have a safety factor. You need to solve then, and all those things comes into picture, and then things become a little heavy, right? But these are generally available in the codal provisions. Okay. Yeah, so that's how you do it. Yeah, one way to do it this is with this, and when you do it like this, you call it reliability based design, not design optimization. The optimization term is now missing. You only call it reliability based design. Okay, so RBD. Now this portion, reliability based design, I'm not going to cover, or I might cover, let's see, but most probably I'll not cover. But there is a homework problem in homework 5, and Haldar and Madhavan actually has a quite lengthy derivation, and all those things are quite detailed there. You can refer to that and do it and learn it. So this is the self-study portion again, right? Reliability based design. What I will rather want to focus on is the other two things that are there. which I will start now. Okay. Okay. So this reliability based design is fine. The idea is that you don't solve an design and the uncertainty problem. You rather multiply your load and all those things by 1.5 or some factor, and then do a deterministic design for that. In a nutshell, that is the whole idea. How you come up with this factor, that's the real mathematical part that you will learn from the book. Will not go there, okay? Or I will not discuss that, but that's in homework 5. Okay. Now, as I said, this is kind of ad hoc. If you want something rigorous, this is not something you will like to have. So what you will like to do is a more rigorous way of doing things, which actually is quite apparent to you by looking at the formulation. Okay, this is what it is doing, right? And there are two ways of doing it. One is known as reliability based design optimization. Not reliability based design, but reliability based design optimization. This is known as RBDO. Okay. There, the high level idea, we'll talk about in details, but the high level idea is that, can you tell me? Okay, let me see if you can tell. Suppose this problem, okay. What is uncertain in this problem in reality? Can you tell me? X is uncertain. What about D? Is D uncertain or certain? D will be having manufacturing uncertainty, because whatever you design for while manufacturing might not be exactly the same. So D is also uncertain. So that means this D star should actually be mu of D star. That means you are designing for the mean and you are assuming that, okay, manufacturing uncertainty only 5%. So whatever you design for, it can vary by plus minus 5%. So when you buy something, you see that the value is plus minus 5%, that is this one. But you will try to find out the mean. So D star will become mu of D star. You will try to minimize C, which is the cost. Okay. And hopefully the idea in most reliability based design optimization is that C is only function of D. In RBDO, this C is only function of D. Why? C is cost, right? Cost of your car is proportional to the amount of material used in the car, because there will be some per unit cost, which is proportional to the how are you designing the car. If you make it, let's say, longer, then you need more material. If you make the plate thicker, you need more material, and that will go to your cost component. So this cost part is kind of deterministic. It can be random also, but let's not go there for now. Okay. So because that will go there later. Okay. So that part is the cost part is deterministic, function of mu D. Okay. Now because D is slightly varying, that cost will also vary, but you will not pay for that. For example, because it is manufacturing, right? You wanted some thickness of 5 mm. Because of defect, they have made it 4.5 or 5.5. Let's say 5.5. But you will pay for 5 only. So that will not account for the cost. So the cost will not increase because of that uncertainty. That will come later. Wait. So I'll come there. Performance will, in the RBDO, performance is sitting somewhere else. So give me a minute, I will be there. Okay. So you will try to minimize the cost. Okay. And here cost is cost. Now you're talking about performance. Where will the performance go in this case? Performance is this H. You don't want the drag and lift to be less than or more than some value. Performance is this H. Again, you don't want the safety to be compromised. So that means the stress developed because of drag and lift, the pressure field that is developed should not cross a certain threshold. So here is the performance setting in the constraint, right? You can. but generally that's not how engineering problems happen in most cases, because as an engineer, we are supposed to design something that is the best cost effective while for satisfying or some performance criteria. But it is done in many cases. For example, Formula One car. There it is switched. You have certain cost constraint, the cost comes into the constraint, and you want to maximize the performance. That will happen in Formula One, right? Some luxury car, Rolls Royce, they will probably don't care about the cost. They will say, I want the design, the aesthetic, exactly. The aesthetic to it will be there, some cost function, and then other things will come there. Possible. It is absolutely possible, right? So in the RBDO setting, I am talking about the setting where the cost is there in the cost function or the objective function. But it is very well possible that will also become random. But anyways, in our setup that we are talking right now, P is your cost, literally cost, right? And your performance of everything goes into the constant, right? And performance means, because we are talking about reliability, it will be some safety performance in most cases, right? In most cases, it will be some safety performance because probability of failure will come into picture. So I want to make it reliability based. So that performance, so this H will now act as my limit state. Stress should not exceed a threshold. That's a limit state. So this constraint function, you will convert it into a reliability constant. The probability H is increasing or less than this is greater than some target reliability or something like that. Right? So the reliability part will come into your, this constraint part will be converted into a reliability constant. And the bound will remain as it is. The idea is simple. In reliability based design optimization, you convert your performance constraint, which becomes your performance function also. You convert your performance constraint into a probabilistic one, into a reliability analysis one, which means, and now things will get trickier, that the reliability analysis part is now an inner loop inside the optimization loop. The optimization loop runs for 1,000 times. Some gradient descent, think of that like that, right? And for that 1,000 times, each of the time you need to compute a probability of failure, which means within each of the iteration, you will probably run your solver 1,000,000 times. So your total number of solver run is now 1,000 times million, which means reliability is expensive, optimization is expensive. But reliability based design optimization is several times more expensive because it multiplies the cost of both. It's a nested loop. Two for loops we are looking at, one for optimization, one for reliability analysis, which means it's nested, it gets multiplied. And as a result, reliability based design optimization is very, very expensive. And that is actually the reason that many people opt for reliability based design. That's simple. Just give me that factor and I will design for it, right? So that is the reason. Yeah. You can. And that's what you will have to do. That is the homework problem you will have to do. But the idea is that surrogate models should be able to cover, let's say, different values of d and x, because for each iteration, remember the d is changing also. So the d should also go inside the surrogate model, and even a small error in your surrogate model changes the direction of your optimization loop, and that is very sensitive. But yeah, we do that, but you have to be careful with constructing the surrogate model. You might need to refine it a few times. Otherwise, the small error that keeps on propagating through the gradient, because you will convert into Lagrangian and go there and take the gradient, and that propagates and creates mayhem actually in some sense. Okay, mayhem. Okay, so that is the idea.
So, this design of this kind of design of experiment really plays the major role.
I mean, in design of experiments play a major role in any construction of surrogate models, because you want to construct an accurate one.
Because it is sensitive to the optimization.
True.
You have to choose that way.
True, but you cannot, because you don't know the values of D, it will go to next. So you will have to go with this exploration, exploitation, and all those things. But you actually do not know what is the next value of D it is going to take. So one of the ideas is that you take a value of D, construct a small area, form it, and then when the D is quite far away, you again retrain it. So all of those strategies are there, but it's really an expensive problem. Yeah. Okay. The question was that design of experiments become more important in this case. I said design of experiments is anyways more is very important in getting a accurate surrogate model. Not only in this case, in any case, right? The design of experiments for training your model, right? Because you will don't know where the D will go next a priori. You cannot construct it based on those Ds, but you can think of some adaptive schemes. Anyways, so that was reliability with design optimization. So in our video, the idea is that you minimize D or mu D arg mean, let's say D, C of D, subject to some reliability constraint, subject to, let's say, probability H D comma X is greater than, so it's violating the constraint, right, for failure, greater than H threshold. This probability should be less than equal to some very small number, let's say 10 to the minus 4 or something like that. So I'll say call it probabilistic threshold, right? And in this setup, obviously you can understand, because I wrote D, that means I'm only assuming X to be random. The manufacturing uncertainty I'm kind of ignoring here, but you can write it mu D, and then the manufacturing uncertainty comes into picture. Okay, and obviously this D will be between lower limit less than equal to D less than equal to upper limit, right? So this will be the kind of problem statement that you will encounter in reliability based design optimization. And in this case, what is happening? Let us see. Okay, so now in the deterministic case, the optimum was here on the line, right? Because you have taken this reliability constant, the objective function will be, the optimum value is pushed towards the safe region. You see, it is now away from this boundary, which means the probability of failure of violating that has now reduced. And the higher threshold you take, I mean, the smaller the probability you take, the more it will move away from the boundary. So this is what will happen. Instead of coming at this point, it will now move away to some other point, which will not be on the boundary now, and that will basically govern your probability of failure. Cost will obviously increase. If you want a safer design, you cannot get at the same cost. There is always a trade-off in life and in anything, right? When you have to pay more to get a safer option. I mean, as simple as that. So obviously, this cost that you are getting is higher than the cost that we are getting on in usual deterministic optimization, right? DDO. But yeah, but if it fails, what is the point of saving that cost, right? It's like you are sick, you will go to a doctor, and doctor is very costly. You say that is costly, I'll not go to a doctor. I mean, what is the point? Keep on being sick. I mean, that is something like that, right? So that is the idea. Correct. Correct. But the most important part is that you know how safe it is. You are controlling the probability of failure, and if needed, you can solve this problem again to get a more safer design. So it is in your control, and that's the most important part. And you know what exactly is happening, what it is designed for. It's everything is white, it's not black box. It's not ad hoc. Everything is known to you, and you know exactly what is happening here, right? Yeah.
have a constraint on h, x, comma, t that then equal to before like reliability fields that I mentioned, we first find out which boundary it is lying on, and then we like
change the value of threshold.
and then again find the constraint over the iteration we will be able to
Search for a method known as threshold shift method. It's a paper, actually my paper only. We did exactly that, where we shift the threshold so as to ensure certain reliability. What you are saying? Yes. Yes. So look at that, and that's a single loop kind of thing. You keep on shifting the threshold. So there are different ways of doing it. What I'm talking about is the most fundamental, the basic way. So now the whole idea is that can you remove one of the loops? The best thing is you remove one of the loops and then work with that. So that there is a whole idea of single loop RBDO. Threshold shift method is actually one of those. There is other also, but that is one of those. Okay.
is there any limitation to that?
Yeah, finding that threshold is often very difficult in a non-convex setting and all those things, right? So there is. But yeah, we were very happy with it. So I did it during my postdoc as a independent work with my friend. But yeah, not exactly, because we're not finding a reliability, we're setting threshold. In subset simulation, we decide the threshold to find the reliability. Here we are not doing that. Here we are shifting the constraint threshold somehow. Okay. So there is motivation from there, but it's not same. Okay.
You were saying shifting, but shifting itself we don't know where to shift and all that.
Correct. Correct. So that is the whole idea, that you have, we develop some strategy that will allow you to do that. Okay. Probably I'll cover that in one of the lectures, this threshold shift method. Okay. Which part? Yeah, it's simple, right? So you see the original point was here, right? Which is on this boundary. You can follow? Which means if there is uncertainty, this red line is the, let's say, the uncertain area, right? So you can see that there is 50% chance at least, assuming it is symmetric to be, that it will fail. 50% is a very high chance. Everyone agrees, right? You don't work on 50-50. In this case, what happens? This point, because you are doing some, incorporating some reliability constraint, look at this, this had moved to this green point. Exactly. As a result, this red area now seen in the failure zone is very small. And this small area is governed by what probability threshold you are setting. The stricter you are, the more it will move in this direction. Maybe from here it will come here, you don't know. But it will start moving and all those things, right? Based on that. Exactly. So that is the whole idea, right? Okay. So this is the whole idea of reliability based design optimization in a very broad sense. Now, how do you solve it? There are two primary methods. One is known as RIA, which stands for Reliability Index Approach, RIA. The other one is PMA, Probability Measure Approach. And then I came to the modern ones like shift, right? Threshold shift method, TSM. And there are others also, by the way. Okay, these are like three I'm saying very broadly. So there are methods of solving it, but essentially you are solving an coupled problem. It's up to you if you can make it uncoupled by some assumption or some way, but it's by definition a coupled problem. Okay, you can come up with strategies to make it efficient, but it's a coupled problem, right? So this is one of the way of incorporating uncertainty. Okay, and obviously in the context of this course, this is the most important one. There is another way of doing it, which is known as robust design optimization, or RDO. The previous one was RBDO. This is RDO, and there is RBD also we talked about slightly. In RDO, the strategy is something else. The strategy now you don't care about reliability, but you care about sensitivity. Can we find a design point where even if the design variable is perturbed, the objective function will not change much? I'll repeat. In RDO, or robust design optimization, the idea is to get an insensitive design. What does insensitive mean? You wanted to design for 5, it becomes 5.5 because of manufacturing, let's say, and then there is uncertainty. So what you will want is that, let that be there, I cannot control that. But my objective function should not change even if this value is changing by much, which is insensitive. Even if the input is changing, my output is not changing. That means it is robust. Robust means perturbation does not impact my final outcome. So that is the idea. So this is insensitive design. I'll not tell you today how we do it, but we'll do that in this maybe tomorrow. But I'll give you one small figure and I'll end it there. So suppose this is my design variable, one design variable, okay, and this is my cost function, which here is actually performance function, okay. And let's say okay, this is how the cost function varies with design variable, and obviously you can understand I took it in a very specific manner because I want to focus on certain things. Let's see. So now, what is the optimum point? This one. Everyone agrees this is the optimum point. So this one. Now let's say I change it by this amount. How much the objective function is changing? From here I'll say this one is huge, right? So in RDO, the RDO will try to find a point, let's say this point. It's also one of the local optima, right? You change by the same amount. By drawing is not same, but you know what I'm trying to say. What is the change in your design variable? Almost zero, but not zero, but very less. This point is an insensitive design point, right? This is a robust design. And again, you can see that you are sacrificing on some cost. This one is more expensive than the other one. So nothing comes for, there is no free lunch, right? You have to pay the extra cost, but that is better than this one because even if your input now changes, you are safe. Your objective function will not change much, which in this case is performance, obviously. So this is the idea of robust design optimization, where the idea is that minimize propagation of uncertainty. Okay, we'll start with this and wrap up this discussion on RDO tomorrow. Yeah, we'll start with this, wrap up our discussion on RDO before going into the detailed math of one of this. I'll see which one we start tomorrow. Okay, but broadly you can understand that in RVDO you are trying to design while ensuring some certain level of reliability. In RDO you are trying to minimize the propagation of uncertainty from the input to the output, from the design variable to the output, from the random variable to the output, right? Now coming back to conclude your part, let's say my cost function is a performance. I can still solve, but there will be multiple performance. One of the performance is my cost function. The cost is a constant and there are other performance which are all in the constant. Possible? In that case, what will I solve? I'll solve RBDO, which is robust reliability based design optimization. Right? Where I will try to make it robust against the objective function while making it reliable against the other performance function. We'll talk about that as well, not today obviously, but so that part, as I said, will come. Okay, so that is known as robust reliability based design optimization, RBDO, combination of both. Lastly, in RBDO, what are you changing? You are changing the constraint, right? Constraint, you are making it probabilistic. In RDO, what you are changing? You are changing the objective function and also the constraint, but primarily the objective function, because you are trying to reduce the sensitivity. So the objective function will change. How? We'll see next time. But you can understand, because C, right? You want a C where it is not varying much. You can imagine that the objective function will change somehow. Okay, so one is playing with the constraint, the other one is playing with the objective function. Combine the two, RR video plays with both. Okay, any question? RR video, yeah.
So that will not go to this point.
That may be somewhere else, I don't know. Yeah, that point may be somewhere here. Somewhere here, or we don't know. Maybe it will come later, I don't know. In this diagram, that point might not be. That in this diagram, maybe that will be the same point.
It is not possible at all that minimum where the B got the minimum there be.
No chance. No chance. If you get that, that is the best case scenario. But that is the scenario where your uncertainty is so less, it does not matter. Even you should not solve a RVDO or RDO problem. That's the case, right? But in a real problem, that will not. Okay. Thank you.